Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, today we're diving into something that's been making waves in the AI world, Google's Gemini 2.5 paper, and the frankly insane number of authors attached to it, 3,295. I mean, seriously?
Insane is definitely the word. My initial reaction was skeptical, to put it mildly. What's actually going on here?
Yeah, it does seem a little excessive. Reminds me of those physics papers back in the day with like 1,000 names from the Large Hadron Collider. Is this just the new normal for big AI projects?
Well, thinking from a neuroscience perspective, this is fascinating. Could this be reflective of how the brain functions? Maybe this large collaborative undertaking is a reflection of how neural networks communicate and learn from each other, not just from data, but from each other.
That's an interesting point, actually. Maybe the complexity of these models necessitates this level of distributed effort. Think about it: data collection, pre-processing, model architecture design, training, evaluation. Each of those steps could involve dozens, if not hundreds, of specialists.
Okay, but I still think it points to an underlying problem. If you need that many people, are you truly optimizing the learning process? Or are you just throwing bodies at the problem because the fundamental approach is inefficient?
Exactly. It feels like brute force, like they're just connecting a bunch of existing representations, hoping something intelligent emerges. I wonder if they're actually creating new universal representations of anything.
Well, that's the big question, isn't it? Are we just scaling up pattern recognition, or are we actually approaching something resembling general intelligence? I'm leaning towards the latter, personally. With enough data and compute, these models can learn incredibly complex relationships.
I'm not convinced that just scaling up is the answer. What about the symbol grounding problem? If these models aren't connected to the real world, how can they truly understand anything? That paper from 1990 feels more relevant than ever.
That's what I'm thinking. Deep learning is fantastic at finding correlations, but it struggles with causation and abstract reasoning. It's missing that crucial connection to meaning.
Okay, but look at large language models. They seem to be exhibiting emergent symbolic behavior. They can generate text, translate languages, even write code. That suggests they're learning something beyond just surface-level patterns.
But is it true understanding or just a sophisticated imitation? Can they truly reason about the world in the way a human can?
And how do we model the dynamic interplay between neural circuits and symbolic processing in a way that reflects the brain? I think that's a critical area of research.
I think we need to explore neuro-symbolic architectures more deeply. Hybrid systems that combine the strengths of neural networks and symbolic reasoning. That might be a promising path.
Yeah, I agree that incorporating structured knowledge is important. But how do we do that without losing the benefits of massive data and complex pattern recognition? That's the challenge.
Maybe the key is in how the model represents and translates between different coordinate systems. Spatial, temporal, abstract. If we can crack that, we might be able to build in true understanding.
Coordinate systems? That's an interesting way to put it. Can you elaborate?
Sure. Think about how we perceive the world. We have visual coordinates, auditory coordinates, tactile coordinates. Our brains are constantly translating between these different representations. Current AI, especially deep learning, feels like it's stuck in one coordinate system. It can process images well, or text well, but it struggles to seamlessly integrate information from different modalities.
The brain integrates information from multiple senses so effortlessly. It's incredible.
So, you're saying that the understanding piece comes from being able to map information between these different coordinate spaces effectively?
Exactly. And the algorithm that can do that efficiently, that's the key to AGI. Deep learning, in my opinion, is just brute forcing its way through this problem with massive amounts of data, but it's not fundamentally solving it.
That resonates. It's like trying to learn a language by memorizing every possible sentence, instead of understanding the grammar and vocabulary.
Okay, I see your point. So, instead of just adding more layers and parameters to a neural network, we need to focus on developing a core algorithm that can intelligently manipulate and translate between different representations.
Thinking back to the brain, how do different brain regions communicate and exchange information? That might give us some clues.
Exactly. Look at the hippocampus, for example. It's crucial for spatial navigation and memory. It seems to be able to create and manipulate cognitive maps, which are essentially abstract representations of space. Can we build something similar into AI?
So, instead of focusing solely on pattern recognition, we need to build in mechanisms for creating and manipulating these cognitive maps or abstract representations.
And that's where symbolic representation comes back in, right? Because those cognitive maps are essentially symbolic representations of the environment.
Yes, and the grounding problem too. How do those symbolic representations get connected to actual sensory experiences?
Okay, let's bring it back to the Gemini 2.5 paper. Knowing what we've discussed, what are the implications of having 3,295 authors? Does it point to a weakness in their approach?
For me, it confirms my suspicion that they're relying too heavily on brute force statistical correlation. They're throwing a massive amount of resources at the problem, hoping that something intelligent emerges, but it's masking a lack of true understanding.
I think it highlights the limitations of current deep learning architectures when it comes to translating between coordinate representations. If the core algorithm was more efficient at that, they wouldn't need so many people to fine-tune and connect all the different components.
But isn't it possible that this is just the future of AI research? That the complexity of these models requires this level of distributed expertise?
It could be, but I think it's also important to ask whether this level of complexity is necessary. Maybe a more elegant solution, inspired by the brain's architecture, could achieve the same results with fewer resources.
And a smaller team. Imagine trying to coordinate 3,295 people. The overhead alone must be astronomical.
It also raises questions about reproducibility. How can other researchers replicate this work with so many moving parts and dependencies?
That's a really good point. Reproducibility is crucial for scientific progress. If these models are so complex that only a handful of organizations can build and train them, it could stifle innovation.
The distributed nature of Gemini 2.5 also raises questions about how the researchers divided the design, implementation, and analysis of different neural structures.
Okay, so let's say we're all starting our own AI research lab. What would be the first thing you'd focus on, given our conversation?
I'd focus on developing novel neuro-symbolic architectures. I'd want to explore how to effectively integrate symbolic reasoning and structured knowledge into neural networks, and focus on building models that are more interpretable and explainable.
I would investigate the biological underpinnings of intelligence. I think we need a deeper understanding of how the brain processes information, especially how it handles the symbol grounding problem, and incorporate those insights into AI design. I'd start by researching how different brain regions communicate and exchange information, and how different neural networks learn from each other.
I'd focus on developing a core algorithm that can efficiently translate between different coordinate systems. I'd research how the brain represents space, time, and abstract concepts, and try to build those capabilities into AI from the ground up. Also, I'd research how different coordinate systems are used and represented in biological systems.
And I, ever the optimist, would continue to explore the potential of deep learning, but with a renewed focus on incorporating structured knowledge and grounding representations. I'd look into ways to bridge the gap between symbolic and sub-symbolic representations, and to develop more efficient and interpretable models. I would want to incorporate more structured knowledge, like symbolic reasoning, into deep learning models.
So, less brute force, more finesse.
Exactly, less brute force, more elegance. We need to find a more principled way to build intelligent systems, instead of just throwing more data and compute at the problem.
Thinking about all this, maybe one future research direction would be analyzing the tasks each group of authors in Gemini 2.5 performed to discover new ways to represent and process information in ways that resemble how the brain's modules might communicate.
Good point. I'm really wondering how many distinct coordinate systems were used in the Gemini 2.5 model. Understanding the dimensionality and the nature of the conversions between them might shed light on whether the current approach is robust.
And I'm still curious about how much of the 3,295 authors' work was focused on data collection and preprocessing versus the model architecture itself.
And more broadly, what specific symbolic representations, if any, were used in the development of Gemini 2.5? If the core is purely statistical, what are the limitations this puts on the algorithm's generalization capability?
Lots to think about, and lots of research to be done. It's clear that the path to AGI is far from settled, and there are many different avenues to explore. This Gemini 2.5 paper, with its army of authors, is just a snapshot of where we are right now.
Right. It is a snapshot in time of a very complex and quickly evolving landscape.
And hopefully, a reminder that bigger isn't always better.
Indeed. It's time to start thinking differently about how we build intelligent machines.
All right, that's all the time we have for today. Thanks for joining us on Cognitive Spirals, and we'll catch you next time.